Hello, my fellow Git nerds. I'm Derrick Stolee, an engineer at GitHub and a Git contributor. Today, my goal is to popularize an idea. Git is the distributed database at the core of your engineering system. When you think about it, Git is the center of your collaboration infrastructure. Not only does Git allow multiple developers to do concurrent work on the same repository, but it also links with your build and test infrastructure, determines which versions you deploy to production or release to customers, and stakeholders in your organization may watch your repository to measure activity and progress. All of these activities coordinate using Git as a communication medium. As a parallel, your application database is the core of your application infrastructure. To persist application data, almost all applications use a third-party database application. This database stores the information that is manipulated and served by application services. Background jobs process data async from user requests. Your infrastructure may have built custom backup procedures with failover remediation. Let's also keep in mind that the database health is monitored by support and SRE. This leads to engineers learning a lot about how application databases work. There are thousands of books about how databases work and how you can write applications that take advantage of their strengths. No one bats an eye at the work required to understand your database and interact with it properly. Huge investments are made to build extra infrastructure around the database to make sure it remains healthy as your application grows. And I'm here to say that everyone should learn about Git in the same way. So here's my personal pairing of database concepts to Git concepts at the highest levels. At their core, databases store tables of data. Git stores objects in its object store. We manipulate and access database information using queries. Git's query language is its command line interface. Databases use specialized query indexes to speed up certain queries. Git has advanced data structures specifically for speeding up certain kinds of Git commands. Distributed databases have custom ways of remaining consistent and dealing with concurrent changes across database nodes. Git repositories communicate through fetches and pushes to synchronize after the fact based on user demand. Finally, when databases need to scale beyond the limits of a single node, application developers can use one of many sharding strategies. Git has similar strategies using multi-repo organization. And by this, I want to equip you with a framework and a vocabulary. You can use these parallels when describing advanced Git features to your fellow developers, and hopefully starting from the common understanding of application databases will help bridge the gap to the Git concepts. Today, I'll talk about my favorite parts of these concepts. Let's start at the beginning with Git's object store. The main storage of Git repositories can be considered as two database tables. The object store has two columns, an object ID and object data. For a given row, the object ID is the hash of the object contents column. This makes the object store a form of content addressable storage. It's not too helpful to need the contents of what you're looking for before you find it, so Git has another table providing starting pointers. The reference store table has two columns, a reference name and an object ID. The reference name is the primary key. These human-chosen names are pointers into the opaque object store, allowing us to gain a foothold into the contents. In this example, the refs tags v2.37.0 reference points to an object in the object store. That object is an annotated tag, which points to a commit in the object store. That commit specifies the object ID of its root tree. That tree contains an entry for the readme.md file, whose object ID points to a blob. That blob object stores the file's contents. We've just taken several jumps through the object store just to find the readme for Git 2.37.0. We can review this lookup in a more abstract way as walking the edges of a graph. First, the reference points to a tag object. The tag object has an object pointer pointing to a commit in this case. Commits have pointers to their parents and to their root tree. And tree entries point to other trees or blobs. We follow the entry for readme.md to find the contents for that file. I'll use this representation for the rest of the talk. Specifically, circles are commits, triangles are trees, and boxes are blobs. When seen in aggregate, the Git object graph can look like this. I'll keep the commit history grouped at the top with a row of root trees below. As we go deeper into subtrees, we find that some tree entries are shared, so despite storing snapshots of work trees at each commit, many of the trees and blobs at two commits are actually shared. This Merkle tree representation is the first way that Git keeps its object store small as users make changes. However, if we're storing full copies of every version of every file, then that would also grow too quickly for most use cases. Here, I've grouped some of the objects that appear at the same path across multiple commits. The top row of root trees all represent the base directory of the work tree. These 3 blobs at the bottom might represent the same source code file. One thing Git can expect is that these objects share significant portions in common, because as software developers, we tend to modify a small portion of the repository at a time. Git uses a particular kind of compression when objects have a lot of common data: delta compression. Here I'm showing an example tree object as the base object, as well as an example delta object. Deltas are instructions to help construct an object based on copying regions from a base object and writing new regions at certain points. We start by copying the initial segment of the tree up into the object ID of the Git version gen entry. Then we write a new section of data corresponding to a different object ID. Finally, we copy the remaining data from the original tree, starting with the file name for the Git version gen entry. At the end of this process, we have constructed the decompressed object, but used significantly less data to store the 2 objects than if we did not use delta compression. This type of compression works quite well for trees, but also works well for most blobs, assuming blobs store plain text files such as source code and documentation. Git has a custom file format that can take advantage of delta compression: pack files. Pack files store multiple objects by concatenating their contents into a single file. The objects are packed together. In addition to full object contents, deltas can also be stored, as long as their bases are also in the pack file. This on-disk storage is not the only way Git uses the pack file format, though. In fact, the format used to store compressed object data on disk is also used to share objects over the network between repositories. Let's explore how repositories synchronize efficiently. The following process outlines the behavior between a Git client and a Git server during a git fetch command. First, the client asks the server for the ref advertisement, which is a list of references and their current object IDs from the server's perspective. The client takes this information and decides which references are important, as well as which object IDs are not present on the local machine. The rest of the communication is done via object ID, in case the remote server changes ref positions. The client then sends a list of object IDs, each of which is marked as a have or a want. The want IDs are objects that are not in the client repository, but are referenced by interesting refs. The have IDs are objects that are in the client repository, and the client guesses are also on the server repository, based on previous records of the server's references. At this point, let's take a look inside what the server is doing. Here's an example object graph, including commits, trees, and blobs. Suppose the client sends one have and one want. It wants the commit A and has the commit B. The server infers that the client has everything reachable from the haves, giving this region of objects. The server then determines which objects are reachable from the wants, but not reachable from the haves. These are the objects the client needs. Back to the server-client interaction, the client may send a small number of haves and wants, but really desires a large set of objects. The result is that the server sends a pack file filled with object data. This pack contains the objects from that object graph walk that are reachable from the wants and not reachable from the haves. This process allowed these 2 repositories to find a set of objects that the client needed without each side listing their full contents. This synchronization is specialized to use the object graph in creative ways. In addition to only providing the newer objects, the pack file sent over the network can also use delta compression. These deltas can use offset deltas that point within the pack file, but also reference deltas that can point to a base object ID that is expected to be present on the client machine based on the list of have objects. This allows even further compression during synchronization. You might be thinking, it's nice that Git has my back and is doing smart things under the hood, but what can I do about this? Well, you are in control of your repository. You determine its shape, and you can influence the norms of your organization. So I have 2 quick tips to share with you today. The first is that you should run git maintenance start in your favorite repositories. This will start fetching from your remotes on an hourly basis, reducing the time spent synchronizing in your foreground git fetch operations. It also repacks your object store incrementally on a nightly basis to keep things running smoothly and reducing the disk space required for your repository. The second is that you should practice good repository hygiene. You want to take advantage of Git's delta compression whenever possible. The good news is that files that do not compress well also do not tend to diff well or merge well, so they do not present as reviewable changes in your pull requests. To fix this, you should remove large binaries from your repositories, especially those that change often. Also, you should avoid committing files that are created by your build process. Only store build inputs in your repository, not outputs. I have a quick overview I want to give to you about macro-scale repository organization. It comes from the concepts of sharding databases when application databases grow larger than what a single node can support. Before talking about sharding strategies, I should first mention that the lack of sharding is the basis of the monorepo pattern. Monorepos are a great idea if you're careful in using good repo hygiene. As your repository grows, it becomes more important to use the advanced Git features that allow focusing on a small subset of the repository, like partial clone and sparse checkout. I've talked a lot about monorepo scale in the past, so let's talk about these sharding strategies. There are different ways to shard your repositories, depending on which works best for your situation. Each of these strategies takes inspiration from database sharding strategies, such as vertical sharding, horizontal sharding, and sharding of time series databases. Unfortunately, I don't have time to go deep into these strategies today. I wrote a 5-part blog series on the GitHub engineering blog that goes super deep on all of these concepts. Hopefully this talk inspires you to dive deeper into these ideas or to use them as reference in the future. And if you remember nothing else of what I've said, let me maybe repeat the core concept that you should remember. Git is the distributed database at the core of your engineering system. Thank you.